I want to continue talking a little bit about this strategy in chapter 9, and we described this section 994 algorithm, which I recommend for computing the a competitive equilibrium for a complete markets model with in our setting with arrow securities, one period arrow securities. So we talked about taking the indirect route, and our general theme, what we're talking about now, is Bellmanizing this model. So we're making assumptions that give rise to a Markov decision problem for the consumers that live in this economy. Okay, so I want to. So the key, I want to complete the Bellmanization step, because we can actually do a little bit more. So the key step with taking this indirect route is the first thing we compute the competitive equilibrium. Actually, all I need is competitive equilibrium allocation. So I actually didn't even need the prices, but compute the competitive equilibrium allocation of the corresponding Arrow-Debreu economy. And then from our equivalence results, we know that can be the equilibrium allocation of the competitive equilibrium with trading arrow securities. Okay, then we did that. We got some formulas. And one thing we did is we got, oops, and there's actually a typo, huge typo. I'm glad I stopped here. We got the, we computed debt limits. There's no beta here. We computed debt limits by solving this Bellman equation. There's our Bellman equation. So now we got the debt limits, and now we're going to we want to compute portfolios. So we want to solve another Bellman equation. So now what I'm going to do is I'm going to write down that Bellman equation and stare at it a little bit. So again, I'm going to kind of use an indirect route. I'm going to use an indirect strategy. So first I'm going to do is I'm going to compute continuation wealth. And I could I could say now I'm computing continuation wealth in an Arrow-Debreu economy. But that's going to turn out to be equal to the same thing as in Arrow Securities economy. They're going to be equal. So I'm going to write that down. I'm going to now write down psi I of S, because I'm in the Markov setting. It's a key thing, the Markov setting. So here's what this continuation wealth looked like. It's a specialization of our earlier formula. Markov state by Markov state, 4-person I. Okay, and now I'm going to, this is the excess of consumption today minus my income today. So that's reflecting that I'm a wealthy person. I can consume more than I'm earning with labor, you could think of. And then I write this down, I of S prime. And I want to solve this for how many values do I want to solve? Well, there's one of these, there's going to be vectors all over the place. We want to, there's how many people are there? There's I of this. So for each person, for each I, S is going to belong to our set S1 through Sn, the state space. So this is going to be n equations in n unknowns. That's what I want it to be. And then where am I going to get Q from? I'm going to get, well, Q I already got for my algorithm above. I've got that pricing kernel. I'm making typos all over the place. Summation S prime. Let's make sure I put this up here. Yeah, I did. Okay, summation S prime. So that's my Bellman equation for continuation wealth. Okay, now I'm going to have to do a little staring now. And so now what I'm going to do is I'm going to, what's my approach? Stare and remember. That's what I'm doing now. Remember. Okay, stare. Well, okay. Good. So the first thing I'm going to stare is, well, the stare part is, I know this because this is exogenous. I know this because I computed it before. Where do I know this from? Well, I'm going to take the allocation from the Arrow-Debreu economy. So I know this. I know this from the, I have to compute the allocation first. So I know this, I know this, I know this, I know the pricing kernel. So now I have a really nice functional equation that I can solve. And I can reduce this to a matrix equation. Actually, it looks like, maybe you've seen this before, it looks like a version, the equation that I have will look like a version of a Neumann expansion. If you've seen that. If you haven't seen it, don't worry about it. What do I mean by that? I mean, I'm going to write this as a vector, psi. I'm going to write this as a vector minus y, I. So these are vectors now. Take out the s. Now I'm going to have a matrix plus q times psi I. And now what I'm just going to do is I'm going to take I minus q psi I is equal to ci minus yi, and now I'm going to take psi I, as I'm going to solve it, I minus q inverse. So now this is an n by n matrix, arranged properly, times ci minus yi. That's how I'd solve that. And the Neumann expansion is under proper conditions. This is I plus q squared plus, which actually these terms have a nice interpretation, which I won't go into now. Actually, I'll briefly mention. Q is this one step ahead pricing kernel. It's as if Q2 is the two-step ahead pricing kernel, three-step ahead pricing kernel, and so on. So this thing is we're pricing effectively by multiplying this. We're pricing an infinite stream. We're striking an infinite stream of future consumptions minus incomes. So this is continuation wealth. So we can compute this. And I'm getting this from the stare part of this. Okay. Now, the remember part is we have to check some things. So what do we have to check? Well, key thing that we have to check is, remember, we start the economy off. We've chosen to do this at a particular state, S0, a particular state at time 0. We did that. And we used that when we computed our initial competitive equilibrium allocation by solving the planning problem. We used that. And that influenced, that choice, that influenced this entire stochastic process. That choice influenced the realization of the entire stochastic process for every person, for all t, for all st. That influenced that starting value. Okay. And then we also started people off. We started everybody off with 0 continuation wealth. Which we could call, that's continuation wealth, which sometimes people call it financial wealth. Milton Friedman would have called it financial wealth. And why? Because, what's that equation? That equation is, that equation just was the time, that thing was equivalent with the time 0 budget constraint for each person in the Arrow-Debreu economy. Check that out. That's the remembering part. We start everyone off with that. Well, think about that for a minute. So this means our solution for psi I, our solution here, which I'm going to get with this Norman equation, that solution must satisfy it has to satisfy psi I of S0 equals 0 for all I for the particular S0 we started economy at. So, another way to say that, take out the mystery, it's got to be true that we've set this thing up so that the Arrow-Debreu, go back to step 1, when we computed the competitive equilibrium for the Arrow-Debreu economy, it's got to be sure that the budget constraint were satisfied. So it's got to be true. So in closing this circle, it's got to be true that after we go through and solve for this recursive representation, this is a recursive, we've Bellmanized recursive representation of continuation wealth. It's got to be true at the end of the day it satisfies this. So how do we know it satisfies that? Where did we build in it satisfies that? And it was right here. We set the consumption allocation, person by person, to what we got from the Arrow-Debreu economy. And then we did this. So nature chose this. We got this from the Arrow-Debreu. And then we computed this thing. Okay, great. So we built it in. So, I'll fire up some Python code, do a couple of examples for this, show you that, this works. So this is built in. Okay, by our algorithm. Okay, now it's going to allow us to prove like a little. Okay, well that's going to imply something. I don't even want to dignify it by a proposition. It's just an outcome that's going to be true in this setup. Okay, so now the next step, this is going to imply something interesting, which I'll tell you about in a minute. So let's go to the next step. This is kind of the final step of our algorithm. Compute the portfolios of one period Arrow securities by solving another Bellman equation. Well, we've actually done that because here's what I claim the portfolio step. I'm just going to equate the portfolio to continuation wealth in the Arrow DeBrew economy. For all I, for all S belonging to S1. That's my claim that is the optimal portfolio. It's a recursive representation of the portfolio that that person chooses. One thing we're going to have to verify, but it's going to be easy. We're going to have to make sure that summation AI of S is equal to 0. So there's no net trades. There's clearing. But this is going to be implied by that we have built in summation psi I. We've built in summation psi I of S I equals 1 through I. We have built that in. So continuation wealths are always going to sum to 0 in the Arrow DeBrew setting. People are just borrowing and lending state contingent with people inside the system. So we've sort of wrapped up this package. Okay, so what we've done, we could conclude this discussion. This has all depended on our Markov chain being time invariant. We've built in a lot of time invariance here. And we started because this chain did not have a T. It was a time invariant Markov chain that stemmed these results. And what we got for this strong result that the person I ends up in this Arrow securities economy. You get these very economical, sparse, parsimonious. We get a pricing kernel that looks like this. It sort of looks like has the same form as a, it's the same shape in Python or MATLAB. It's an n by n matrix, if you will, as a transition matrix. It's actually related to the transition matrix, and in the way you take the transition matrix, multiply by beta times the ratio of margin utilities in state S prime and S. You've got your Q. And then we got person I when when he's in a given state, he chooses this portfolio next period. That's depends on who he or she is, but actually doesn't depend on the current Markov state. Okay, that's a good place to stop.